Okay, this is going to be the last lecture for your summer. Yay! What we're going to do, okay, is take a look at uniform circular motion. I'm going to go over a couple of sample problems, one of which relates back to vectors, which is always good, and then another regular uniform circular motion problem. And after that, normally I would do a lecture on problem solving, but we've done some problems here already. So I think I feel pretty good about the problem solving at this point. I would ask you to ask questions on the blog and just hit me up for any questions that you have. Ask questions a lot. I will be gone the last week before break until about the Sunday before break, because I will be on vacation in Disney. And yeah, maybe I'll check the blog, but I'll be in Disney, so I wouldn't bet on it. Anyway, all right, so now what I'm going to do, I'm just going to show you the equation for uniform circular motion, and pretty much go from there. I'm not going to go through the proof. We already know all this stuff from previously when we did it last year. Basic idea is this: if you're going around in a circle at a constant speed, so this is uniform circular motion. Now let's analyze what this means. Okay, uniform. That uniform means delta V, not delta V vector. Delta V as in speed is equal to 0. Okay. Does not have a vector arrow over top of it. Okay, it has an arrow over top of it, but that's not a vector arrow. Just pointing down here. Circular. Okay, this means that the change in the radius is equal to 0. Okay, and well, it's motion, so I could say it's moving. But uniform circular motion. Okay, we have a constant radius at a constant speed. Okay, so now as something moves around here. This will be right here. This, my vector, and let's just say it's moving in this direction, okay? V always points tangent to the circle. So now V is always tangent to circle. And this is velocity as a vector, because we're talking about specifically its direction. Okay? R goes from the center here to wherever it's located at a particular moment in time. Okay? R is always perpendicular to circle and goes from center of circle to its location. Okay? And finally, the acceleration. Now, one thing we learned last year is that the acceleration, centripetal acceleration, okay, always points inward. Okay, so my centripetal acceleration always, and this is very important, I keep underlining always, because physics, there's a lot of times that always almost never works. But in this case, always works. So now, that's very important when you get into multiple choice type questions on the AP test. Okay? Centripetal acceleration always points inward, not inward, inward from location to center of circle. And it's always perpendicular to circle. Okay? So now, the equation that we have here, okay, my centripetal acceleration is equal to v squared over r. Okay? Remember, acceleration takes a look at change in velocity. Okay? Velocity has both magnitude and direction because it's a vector. The speed is not changing, but the direction is. So even though it doesn't have a change in speed, it has a change in velocity because the velocity is changing. Velocity is changing because it's changing direction. Okay? And the magnitude of the acceleration is v squared over r. Okay? The other thing that they point out in this chapter, okay, is the period, the time it takes to complete a full circle around. And that's going to be the distance, which is going to be 2 pi r, divided by the speed v. Okay? So this is really just distance divided by velocity is equal to time. All right? So that's really the equations that we're going to take a look at here. We could also take a look at omega, but we're going to hold off on that for a little bit. So let's just take a look at 2 questions that they asked, one of which is very short and very important, and something that you can definitely see on the multiple choice. So let me stand over here so you can put those down if you haven't gotten them already. Let's take a look at number 46. Centripetal acceleration addict rides in uniform circular motion with a period of 2 seconds. And radius equals 3 meters. So now, we're going to do, this is like the Gravitron type ride. My kids love it. They're 4 and 6 years old, and we ride this ride at Great Adventure. It's one of the few rides that my 4-year-old can go on. So now, my period is equal to 2 seconds. My radius is equal to 3 meters. So my period is equal to 2 seconds, and my radius is equal to 3 meters. At time t equals 1, its acceleration is 6. I'm going to drop units on this. Okay? The acceleration is equal to at t1, the acceleration is equal to 6 I hat minus 4 j hat. The questions are, Mr. Phillips dropped units. Yes, I did. And you'll see why in a moment. At that instant, what are the values of v dot A? V dot A is equal to what? And R cross A is equal to what? Okay. We're going to make use of this picture here. And also think about what V dot A is. Remember, V dot A, and you've got that, and you say, well, wait a second, I can't get V. I've got A, but I don't have, I've got A, I don't have V though. How can I, and there's no time factor here, how can I figure this out? And there are ways that you can do that. I'm not really going to get into that though. I want you to see something. V dot A is equal to magnitude of V, magnitude of A, times cosine of the angle between them. What's the angle between V and A? It's 90 degrees. So this is equal to V times A times cosine of 90. 0. R cross A. This is equal to the magnitude of R magnitude of A, times the sine of that angle. R points this way, A points that way. What's the angle between them? It's not 0. RA might as well be though, sine of 180 degrees. Sine of 180 degrees, 0. And we're done. Number 46. Okay. One more problem to take a look at, and then we will be done with summer lectures. Woo! Okay, this is actually a non-conceptual problem yet. You're going to have to calculate this. Okay, a rotating fan completes 1,200 revolutions every minute. Okay, so now, we haven't really talked about omega per se. So I get 1,200 revolutions every 60 seconds. Consider the tip of the blade at a radius of 0.15 meters. So I know that the radius will equal 0.15 meters. A, I want to know the distance in one revolution. B, V, that's of the tip. C, the magnitude of its acceleration. And D, and we're just talking about the edge of the fan blade, was a period of the motion. Okay, so let's go ahead and solve this one. Okay, just so we can still take a look at what's going on here. And we're just talking about magnitude, so I don't have to talk about direction. Okay, distance in one revolution. Okay, so for part A, I know that that distance is going to be the circumference. The circumference is equal to 2 pi times r. So that's 2 pi times 0.15 meters. So that distance is equal to 0.942 meters. B, I want to know the velocity. Okay, so now, here's the thing. Really, velocity, you're going to be talking about a distance divided by the time. I don't know the time it takes to make one complete revolution. Not very hard to figure out. I don't know the distance that it makes in 1,200 revolutions. It's not very hard to figure out. I can just do one or the other. So now, the period here, well, I think that's the way I'm going to go. It's, think about what the period is. It's the time it takes to complete one revolution. Okay? So period is going to be 60 seconds divided by 1,200. Okay? It doesn't have to be 2 pi r over v. Okay? You think about this. Okay? It's the time it takes to complete one revolution. Well, I complete 1,200 revolutions in 60 seconds. So one revolution will be 1/1200th of 60 seconds. So I do that. See, 600 over 1,200 would be 0.5. So this is 0.05 seconds. So now, by the way, that's D. So now B is going to be 0.942 meters divided by 0.05 seconds. So my velocity, all I'm going to do is multiply this by 20, so I get 1884. Put the decimal point there, and this is going to be meters per second. C, okay, this is going to be, my acceleration is going to be v squared over r, so it's going to be 18.84 meters per second squared divided by the 0.15 meters. We are almost done with summer lectures. Woo! Multiply that by 20. 18.8. That's right, 18.85 if you eliminate rounding. I'm going to square it, divide by 0.15, and I get acceleration of, really big, 2369. So my acceleration is equal to 2369 meters per second squared. Okay, and we are done. Done. There we go.